start. How should I start?
I should introduce you first.
Okay.
All right. It is my extraordinary pleasure to welcome my good friend, Jeremy Kahn, for a long time, to be the first Chern-Weil lecturer this year. He is very well known to people working in hyperbolic three manifolds, rational maps, low-dimensional geometry and topology, relations to probability, and so on. He is known for his technical acumen and his creative brilliance, which has been recognized with his receiving the Clay Research Award and being an invited speaker at the ICM in years that I don't remember, but probably in the last couple of decades or so. And he is going to speak on limits of geometrically and topologically random surfaces in hyperbolic three manifolds.
Thank you, Danny. Yeah, it's a great pleasure to be here. It feels like a considerable honor. So I always tell my students that if you have, well, let's even start with like, well, we could have H2, for example, and we could have isometries. This is the blackboard eraser. This is the whiteboard eraser. So, yeah, if we have isometries of H2, that acts, of course, on H2 by isometries. Let's just take orientation preserving. But if we take the frame bundle of H2, then there's also a right action by isometries. And I always say that the group acts on the left by, no, the right action is not by isometries. That's the whole point. I always say the group acts on the left by isometries and on the right by instructions. So there's some sort of normalization, and it's maybe better to just fix a group here, like PSL2R, which is isomorphic to this. And the point is that if you have a frame, then you can rotate the frame. You can do horocyclic flow on the frame, or like geodesic flow in one direction or another. And these are all these instructions that you can perform. And likewise, if we have a frame bundle, if we look at the frame bundle of H3, then we have the group of isometries of H3 acting on the right with some appropriate normalization. And then we have a subgroup of that, which is our PSL2R. And then, of course, we could take a quotient of this by a lattice. We should really write that lattice on the left so we can act on the right. And this is the frame bundle of our three manifold. And it's enough to take two frames if we want to look at this PSL2R action. And so we have this PSL2R action on the set of two frames of a hyperbolic three manifold, again, just by rotating or flowing in one way or another. Yeah, so there isn't much difference, especially if it's oriented. But in terms, if you wanted to generalize it to an N manifold, you could still just take the two frames and act by PSL2R. Or you could even take some locally symmetric space and take appropriate two frames. So, and so we have this action here of PSL2R on this frame bundle. And we also have an action, I don't know, should I keep it on the right side? I don't know. But we have an action of measures on the frame bundle. So M will always be this closed hyperbolic three manifold. So I'm going to say this is co-compact. And then we have an action of PSL2R on the measures of the frame bundle by pushing forward by any of these elements. And we can ask sort of what are invariant measures. All right, and so number one is the Liouville measure. Maybe we want probability measures. The Liouville measure on these two frames. So the Liouville measure, it's this equidistributed measure. It's basically a lift of the standard volume on the three manifold. And the second is measures from totally geodesic surfaces. They could be immersed. They don't have to be embedded in M. Okay, so if you have your three manifold and you have some totally geodesic surface, then you could look at all the two frames. And to be precise, we're taking the 2D Liouville measure. So we could take the 2D Liouville measure for totally geodesic immersed surfaces. And that's another PSL2R invariant measure. We can take convex combinations of above. Okay, and then there's the theorem. I'm pretty sure Ratner, but some people say Ratner-Shaw. The theorem is that that's all. Okay, so these are the only invariant probability measures on this frame bundle. So that is part 1 out of 6. Oh, one last thing. We could also take, maybe I'll just squeeze it over here. So we could take G2M, which is the Grossman bundle. So two planes. In M. And then, I don't know, maybe I'll put it down over here or something. So we have, F2M, the two frames, and then G2M, and then we have, say, SO2R acting this is basically a principal bundle here. There's maybe some orientation issues that I'm ignoring and will continue to ignore. So the point is that if we have a measure down here, we can make an SO2R invariant measure over here. Just look at all the frames. In a sense, take the Liouville measure on the plane. Let's just look at all the frames. And so I'll talk about SL2R invariant measures down here, really meaning SL2R invariant measures of the lift. Do you have a question? Yes?
What do you mean by two planes?
So if we have our three manifold, we could look at any point and then any two planes. So two planes. These are 2D planes. 2D planes in the tangent bundle of M. Okay, so at a point we have a three space and then we have two plane. And so we can lift it up to here and we can talk about sort of invariant measures on the Grossman bundle. So, okay, so that's invariant measures. And, let me say one more thing now. So if we have F from S to M, so if this is a closed surface, then we get, we have a surface, a three manifold, and then the surface kind of wraps around inside here. I can't draw it very well. And then we could look at each point, and we get a tangent space at that point. And we can take the area measure on f of s. And at each point of f of s, we can take the tangent plane. And really, of course, we're taking the area measure. We're pulling it back to here. But anyway, we can just say at each point at f of s, we take the tangent plane. And so we get a measure. Sorry? Yeah, smooth. A smooth immersion. Sorry? Yes. Good points. Yes, if it's not an immersion, then we don't have a tangent plane. Yes. So, so we could call that mu f. Well, after we normalize, we could get the normalized measure sort of for tangent space to f of s. Let me write it that way. So we could normalize to be a probability measure. And, right, if this is not totally geodesic, this is not going to be PSL2R invariant. Things will fly off. Okay, but, and S could be disconnected. It could have many components. Okay, but now we could say, so there's a theorem. I don't know the proper attribution. It's a very simple theorem to prove. So it says that if Fn from Sn to M is a sequence of immersions of possibly disconnected surfaces, Fn, the sort of curvatures, so the curvatures, the principal external curvatures, so we could say principal curvatures of Fn of Sn goes to 0 uniformly in N, and let's say these mu sub Fn's converge to some limit measure, then mu is PSL2R invariant. Okay, so this measure, again, it's a measure, say, on this Grossman bundle, G2M, all the tangent planes.
I think you're saying, okay, so when you say uniformly, it's uniformly on the surface, but you could ask for the weaker statement that the curvatures go to 0 on most of the mass.
We could, but I'm happy with this. This is all we need for the future. Yes, it's a great question, but this is where we are. So, so this is a way of generating PSL2R invariant measures, and we can ask sort of what can we get. And that was a mistake. Okay, so yes.
When you say that it's like you have like a measure on G2 of M,
Yes.
is this related to or the same as like an area form or illumination?
Yes, so we get, essentially we have an area form on the three manifolds. We can pull that back to the surface and we get an area form or measure here. And then for each point, we can look at the image of the derivative and get a two-plane. And so we get a map we get a sort of lifted map, let's call it F hat, from S to the G2 of M. And then we have the pullback measure so we have the sort of area sub M, and then we're pushing forward by F hat and getting a measure on G2 of M. So, Okay, so let's continue. And so the first question, if we say, well, we have a sequence of surfaces, of these immersed surfaces, with principal curvatures going to 0. So the principal curvatures are less than 1 if they're sort of uniformly, well, compact surface. If they're always less than 1, then in fact these surfaces are pi1 injective. And so there's a question of, do these surfaces even exist? And so there's an old theorem of yours truly and Vladimir Markovich. So basically saying for all epsilon greater than 0, there exists f, well, for all m, basically, we're assuming we have an m, there exists f from s to m with principal curvatures. I should have a better name for these. Curvatures. I could just call them PCs or something. Less than epsilon. Okay, that's one way of stating it. So there exist these nearly geodesic immersed surfaces. Okay. So again, immersed surfaces. So, and then there's, using kind of the machinery of this, there's a beautiful theorem of, I think, Fernando Alasal. I hope I'm getting his name right. That says that, for any PSL2R invariant measure on this Grossman bundle, measure mu, there exists this sequence Fn from Sn to M such that the mu Fn's converge to mu. And I think he does a little work and he makes these connected, which is kind of cool. They're compact, yeah, they're closed surfaces. Yes. No. So M, I'm assuming M is compact. M is a closed.
You said that you wanted to connect them.
Oh, the surfaces here.
But the supportive mu doesn't need to be connected.
The supportive mu. Yes, the supportive mu doesn't have to be connected, but these are all normalized to probability measures. So it's certainly possible to converge to something with disconnected support. Yes. Yeah. Okay, we're all agreed on that. So that's a beautiful theorem. I think that was his dissertation. There'll be a couple of dissertations featured in this talk. Maybe yours can be featured in the next talk. So, so let's see. So maybe we can take a brief interlude, and just for fun, we could do it over here. So if we had, say, our 3-manifold M, which I can't draw, and we could look at closed geodesics on M, and I believe if we have any measure on the unit tangent bundle that's invariant under the geodesic flow, then it can be realized as a limit of closed geodesics. I think you can again make it connected if you want. But if we could say, what if we take a random geodesic? So we could take sort of the disjoint union, in a sense, of all gamma such that the length of gamma is less than some constant. And then we could take a measure for this disjoint union, and we could say, what does this converge to? And the answer is this Liouville measure, this Liouville measure on the unit tangent bundle for M. So this is like a kind of basic mixing result or equidistribution result. There's lots and lots of these closed geodesics, and the limit is just the most simple and natural thing. There are lots and lots of invariant measures on the tangent bundle of M. There's a huge array of them. But if we just take the sort of sum of all lengths, all geodesics, and we take the measure for all of that, we get the Liouville measure. So that's motivating the main question for this talk, which is what do we get if we don't just choose very carefully constructed surfaces, if we take random surfaces, or in other words, kind of the sum of a large collection, what do we get as the limit? Yes?
Can you just clarify over here?
Yes.
Measures
So again, right, it's if we take sort of if we think of a gamma from, say, the circle into our manifold, or we could take the tangent bundle of the manifold, then in this case we have a natural, if this is like constant speed geodesic, we could just take gamma lower star of our probability measure on S1, and then this is a measure on the unit tangent bundle of M.
And so the support of this would be the image of gamma?
The support would be the image of gamma in the unit tangent bundle, yes. And so I'm saying if we sort of average all of these image measures, then, yeah, as t goes to infinity, this average will converge to the Liouville measure. Okay. Oh, I'm sorry. Okay. I'll use the black. Thank you for telling me, Danny. Okay, so let's go ahead. We're finally getting to part 2 of the talk. So we want to define some things. So S epsilon, well, there are sort of 2 definitions of S epsilon that will be equivalent for 99% of the purposes of this talk. In our paper, we actually use the set of F from S to M such that F lower star of, so the image of the fundamental group is 1 plus epsilon quasi Fuchsian. And if you know what that is, that's great. If you're not, don't worry about it, because we could also think of it, well, it's not equal to this, but other S epsilon. So another sort of different thing, I don't know, with a wiggle on top, is the same thing here, but with this has these principal curvatures less than epsilon. And these are not exactly the same thing, but they're pretty well related. I think everything here, we could have a k epsilon and vice versa for epsilon small. And for the purpose of the talk, for the purposes of the constructions and the theorems, we could use either of these. And then there are certain subtle things about conjectures that may depend on our choice here. So, and then there's kind of the stars of the show. So we could have S epsilon, let's say, geometric of T, which is a set of F in this S epsilon, such that the area of F of S is less than T. Okay, so that's kind of directly analogous to this hard-to-read red thing, where we, instead of a cap on the length, we have a cap on the area. But then, because we have surfaces, we could also define a topological cutoff, and maybe we'll use a G here. Yes? Ah. Yes. So, So so these are, you're absolutely right. These are homotopy classes, or minimal surfaces.
Are you worried if there's more than one?
Well, there isn't if epsilon's small. So let's say, let's just say minimal surface. And then for epsilon small, which is what we care about, there's unique representative. But it's a very good question. Thank you. Yes. And then our topological estimate is the same thing, but now just that the genus of S is less than G. And here we're taking our surfaces to be connected. So here we should say connected. Okay, so we have surfaces that are nearly geodesic, and our notion of randomness is just to choose one at random. And randomness, I don't know, it's just a buzzword or something where we're really going to take the average of all of this. So we have this mu geo epsilon of t, right, which is, well, there's a couple of ways of defining it that turn out to not make any difference, but let me just say 1 over the size of this S epsilon geo of t times the sum over f in this S epsilon geo of t of mu f. Okay, so we're just taking the average of all of these push-forward measures. Yes?
I think you alluded to this quickly. Does it matter if we normalize like before or after?
Basically, it doesn't. The simple answer is it doesn't matter. And we could even take the sort of hyperbolic, conformally represented hyperbolic metric and use that area form. It doesn't matter. It all gives us the same theorems in the end. And then likewise, mu epsilon top of G equal the same thing. You can fill that out. And then we say suppose, so let's just do the geometric story first. So we could have, so we can say, suppose, so let mu epsilon, for each epsilon basically, let mu epsilon be some limit. So mu epsilon geo be some limit of mu epsilon geo t as t goes to infinity. And then let mu geo equal some limit of these mu epsilon geos as epsilon goes to 0. Okay, and likewise, of course, we can define this mu top epsilon and mu top. Okay, so I guess ideally we'd like to say that these are uniquely determined, perhaps even that these are uniquely determined, that we have convergence. But we're just saying, suppose we take some limit here, and then, so first as t goes to infinity, then as epsilon goes to 0. And we're saying, what kind of limit measures can we get with this area cutoff? What kind of limit measures can we get with this genus cutoff? So now we can state our main theorem. I can keep the attribution. So this older theorem is, I don't know, 12, 15 years old, something like that. I guess about 15 years old. And this new theorem is just, we put it on the archive in 2023. I think that's right. So the theorem is that so every mu geo has mu geo Liouville. So we can ask, what's the contribution of the Liouville part, this equidistributed part? And we can say that this is bigger. This is a probability measure, so it's normalized. It's bigger than some universal constant, completely universal constant, bigger than 0. Okay, so every geometric limit will have some part that's equidistributed. And we conjecture that the whole thing is equidistributed. And on the other hand, every mu topological has this, I'll write it this way. Mu topological Liouville equal to 0 when M has a totally geodesic surface. If M has no totally geodesic surfaces, then it has to be the Liouville measure because it's nothing else that it could be. But if it can hang out at a totally geodesic surface, then it will. So this is enough to say that you can never have this measure equal to that measure, which I think is kind of cool. And maybe right now I'll just write the conjectures. So and so we have conjectures here that mu geo is equal to its Liouville part. So the entire thing is well, let me just say that this mu g is Liouville. And that the mu top is, well, let's just say supported on the totally geodesic surface of minimal genus. Okay? And maybe by the end I'll give some hint of why we believe this. Yes?
If n is arithmetic,
Yes.
has lots and lots,
Yes, infinitely many totally geodesic surfaces. Yes.
apply your theorem to get a corollary that says something about the growth rate of the genus.
So, no. I cannot tell you anything about the growth rate of the genus of the surfaces, but I can tell you that a limiting topological measure, I can give you an explicit bound on how much of its measure is on surfaces of large genus. So it's like 1 over the log of the genus. So I can at least do something. Yes. Yes.
I just wanted to parse the notation here. So this new sub L is just saying you're taking the Liouville measure of the supports of the limiting measure, and you're saying that that's found in the Lesson theorem?
So, okay, so you're right. I should define this better. So this is the Liouville sort of component of the convex combination. Right? We said that every invariant measure is a convex combination, so we can look at the contribution from the Liouville measure. Or in other words, yeah, if we, well, that's what it is, yeah. And so, okay. And so here we're saying there's no Liouville component. So in other words, it's just supported on this countable union, at most countable union of totally geodesic surfaces. Okay, so that's the theorem. Yes?
I think you mentioned you wrote down this theorem that this shows that the geometric and topological measures are
Yes.
different.
Yes.
Is that only the case when M has a totally geodesic surface?
Yes. You're absolutely right. Yeah, if M has no totally geodesic surface, the only possible limit is this Liouville measure. So then they have to both be the Liouville measure. So you're absolutely right. Yes. Yes. Okay. Yes.
So the second part of the conjecture,
Yes.
if there's only one minimal genus, then that means the limit is unique.
Yes.
If you have multiple minimal genus, like the limit actually exists.
It's hard enough to prove this conjecture. I don't know. Let me just say I don't know. Yeah, we'll leave it at that. So, okay. So we have actually 25 minutes left. And
So here's a, I don't think I want to interrupt you very much. But if I have a closed surface,
yes,
of course I have lots and lots and lots of covers of it, super exponential.
yes,
And it's easy to imagine that those terms are going to dominate.
yes.
Is there a way of counting primitive surfaces?
Okay, it's a beautiful...
Maybe it's not a good idea.
No. It's a very good question. Yeah, you could say if we're just taking lots and lots of covers of a single surface, which is exactly what we're going to do, then it sort of seems like cheating. But let's return to this at the end. I believe there is a way to uncheat.
I mean,
By,
if it were number theory, we'd say primes versus numbers. And
yes. No. Yeah, we could look at commensurability classes. So instead of taking all the surfaces, we could basically take all the commensurability classes, or all the surfaces that don't cover something else. So I'll just say in words, I believe that there's a way, if you have some very high genus cover of a single surface, to modify it using our pants construction to make it no longer a cover, and therefore sort of distinguish at the cost of adding bounded genus. And so the theorem should still hold, but that's in a way a conjecture because someone has to prove this. Okay, so let's go ahead. And yeah, it was a great question, Danny, because it anticipates... What is going on? There we go. It anticipates... maybe even I'll use this board, writing in black. So there's two basic counting estimates that we can use to prove these two limit estimates. And the limit estimates at the end of the day are counting estimates. So the first is this theorem of Muller and Puchta. So the theorem of Muller and Puchta. It's proven using representation theory. It's really a truly remarkable proof, I'd say. And so it says that if we look at, we don't have to be able to see this part very well. If we have a surface down here of genus G0, and then we have some very big surface covering it of genus G, and we could ask, how many covers? And there's some question, this is like subgroups or conjugacy class of subgroups. It doesn't make that much difference in the way that we're using it. So how many covers are there? And the answer is, it's like G, well, to be precise, G minus 1 over G0 minus 1 to the 2G. Okay, so this is the number of covers. Oh, sorry, asymptotic. Asymptotic, of course. So the number of covers is asymptotic. The number of covers, of genus G, of a surface of genus G0, it's asymptotic to this. This has to be a whole number. So assuming that's a whole number, then that's the asymptotic formula. Okay? And then there's a second theorem, which is another theorem I proved with Vlad, kind of back around when we proved the first theorem, and it's a very basic counting estimate. And toward the end, I'm hoping to explain the proof of this because it's used in our new theorems. So we could ask if we have a surface now, and we're embedding it, we're immersing it again, immerse, and say pi1 injective. So in particular, if it's nearly geodesic, then it's pi1 injective. If we're immersing it, again, into our three-manifold M, and we fix a genus, let's call this genus G, and we say, how many, say, free homotopy classes? Okay, so how many free homotopy classes of immersions are there of one into the other? This is maybe a little bit blocked, but and the answer, it's sort of close to this one. We just have a sort of very rough answer. CG, well, bounded above, so less than or equal to CG to the 2G. Okay, sorry if that's hard to see. I could swap these. I don't know if that would help. But I could sort of put it up like that. How about that? So we're looking here at covers of a single surface, or in other words, immersions from here to here. And we're looking here at immersions into a three-manifold. And we just get this sort of rough upper bound. But that'll be enough. Well, we'll see. We'll refine that at some point. Okay, so this is our theorem. And the proofs, in a way, yes? Let me see. I think it's basically universal. So there's maybe a multiplicative constant in front that depends on M. I could add a sort of Cm here, something like that, and then I think it's universal. And we'll come back to that. Is it universal? Yeah, it should be basically universal. Yeah. So, yes.
Another question. If we just look at the geodesic ones, if we count by area or by genus, it's going to be the same number because.
Yes. Yes.
And so, but now if we increase epsilon,
Yes.
then for every epsilon, we're going to have, if we count them by genus and by area, we should have more by area than by genus because there's a relation, right?
Yes.
Genus equals area.
Yes.
Equals.
Yes.
So now what you say is, so there are more by area than there are by genus. And so the content is that there are so many more that when you average, you end up getting the Liouville measure, while in the genus there's not enough that they just concentrate on a single.
Okay, so you're sort of let me try to give the proofs. You're definitely kind of anticipating some of the ideas. So let me try to talk about that. So let's talk first about this geometric bound on area. So yeah, we can have a little bit of fun. So right, so for hyperbolic surface, or in other words, totally geodesic in a three-manifold, as you said, we have the area is equal to 4 pi times genus minus 1, right? So we could have a little fun, and we could rewrite this as G equal A over 4 pi minus 1, and we could have a little fun and say T bar is going to be T over 4 pi. There's a plus 1, right? Genus, yeah, plus T over 4 pi plus 1 or something. And And then, yeah, so what we're going to see is, yeah, and in general, what we have more generally, right, by Gauss-Bonnet, what we have is that if we take, again, yeah, this 4 pi times genus minus 1, right, 2 pi times the, minus 2 pi times the Euler characteristic, it's the integral of the intrinsic curvature dA, right? That's Gauss-Bonnet. And let's see, this intrinsic curvature, right, it's the sum of the ambient curvature and the Gaussian curvature, the product of the principal curvatures, right? So, so we have 4 pi times g minus 1 equal the ambient curvature, which is minus 1. There's something backwards here. I guess there's a minus here, but maybe I'll just put it over here. And so we get a plus 1, and then plus, in a minimal curvature the surface, the two principal curvatures are the same. So we get 1 plus the principal curvature squared dA. Right? So we get some extra genus coming from this. It's bigger than the area. It's bigger than the area. And the idea is that by this, the bigger genus we have, the more surfaces we have. So if we can use our little bit of wiggle room to get some curvature and some extra genus, then we can get more surfaces, and those will dominate. So, so let me state some theorems here. So the first theorem, well, let me say I promised you a second dissertation. So this is Rao. I think it was just last year. I'm losing my mind. Yeah, it was just 2024 that he graduated. He was my student. And it's an absolutely beautiful theorem. So it says that for any quasi-Fuchsian group H, quasi-Fuchsian representation say rho from pi 1 of the surface of genus 2 into PSL2C. And gamma subset of, again, this PSL2C co-compact. So gamma Rm here, of course, is just this H3 mod gamma. And k greater than 1, there exists this, I don't know what to call it. I'll just call it a gamma prime subset of gamma and say H prime subset of H, but of finite index. So I guess H colon H prime finite with yes to H, sorry, subset of there. Thank you. With gamma prime and H prime K QC conjugate. So what does this mean? It's saying that if we have a R3 manifold M, and we have some like model surface, and maybe I'll just draw the universal cover, so it could have this kind of crinkly limit set or convex core, and we're able to find a subgroup in here. It's not nearly geodesic anymore. It's kind of as crinkly as this, and just about exactly as crinkly as this. And so instead of being modeled on like a Fuchsian surface, it's modeled on this quasi-Fuchsian surface. But it's still a surface subgroup because we have finite index over here. And it turns out it's much harder if we take genus bigger than 2. But genus 2 is enough. And so there's a corollary to this. And so the corollary is that given M, so for all our, well, given our M and epsilon bigger than 0, there exists this surface, I don't know, let's just call it G epsilon from S to M. So again, we could say a minimal surface, because we can take these things, if they have sufficiently small quasi-Fuchsian constant, we can make them minimal. There exists a minimal surface, G epsilon, that with G epsilon in this S epsilon, so it's, well, say principal curvature is bounded by epsilon, and the, so there exists some universal C, let me say, and with the integral over G epsilon of S of the extrinsic curvature, so we could say this principal curvature squared, bigger than this universal constant, and let's just take it over the size of S. So we're taking the average principal curvature bigger than this universal constant times epsilon squared. So we have some we're really using that epsilon of wiggle room to get some kind of definite fraction of the total amount we could get. And that follows basically because we can take this epsilon of wiggle room and do a little bit of bending and then see that we get some definite epsilon in genus 2. And then if we take a cover that's very close to that, if we take something that's very close to a cover of that, we're going to preserve our average amount of curvature. So that's a very nice corollary. And the consequence of this is the sort of corollary of the corollary is we can get let's see here. Yes, we can get C epsilon t and then 2t slash. That was our normalized thing where we divide by 4 pi to kind of approximate the genus. But then we get something extra. So we get 1 plus, this is a universal constant again, C1 epsilon squared, covers of this G epsilon with area less than T. Okay, because our genus is going to be a little bit bigger. It's going to be a little bit bigger by this. And so we can use just this Muller-Puchta formula to get this many covers. Okay? And then, on the other hand, there's a theorem. And I guess this theorem is from our paper. So I left out poor Smigla. This was actually done jointly with Vlad and Smigla. Smigla? Sorry? Smilga, yeah. I never met or talked to Ilya Smilga. But he contributed really to this part of the paper, so that reminded me of his contribution. There's a beautiful theorem that's really due to Vlad and Ilya, because they can do differential geometry. And, right, so if, say, f from S, well, f in this S epsilon spends at least P, say, in 0, 1, of its time really in the sense of area, near the totally geodesic part of M, or really G2M, then we have some bound on the total genus. Then the genus for this F, in other words, for the surface, is, I could say genus of S, is less than, so the point is that we get this T bar, right, and then we can get some amount of extra, but our extra is going to be controlled by 1 minus P. So we get a C2, 1 minus P epsilon squared. And so what it's saying is, if it's hanging out near the totally geodesic part, it can't really accumulate much total curvature, much of this extrinsic curvature, and so it can't accumulate that much genus. And so if it's only spending a small part of its time in the rest of the surface, sort of free to wiggle around, then we get this upper bound on the genus. And therefore, a sort of corollary of this is that the number of these, right, is then less than, we can use the same, no, now we use this old estimate on the number of homotopy classes of immersed surfaces of genus G, and so we get a constant times T, and then this 2 slash T 1 plus C2 1 minus P epsilon squared. Okay, so we can just directly compare, and it's the exponent here that's going to win. The exponent is going to matter much more than the base. And so we get the final conclusion, which is that, we get C1 epsilon squared. So, what is my... Yes? Oh, okay. So let me just finish up, and we won't be able to talk about the second half, but we're almost there for the first half. So the point is that if P is small, then this is going to win, right? So the C1 epsilon squared is bigger than the C2 1 minus P epsilon squared if 1 minus P is less than C2 over C1. So C1 over C2, I think. So the point is that if it spends too much time near the totally geodesic part, it's going to lose to the covers of the single one. And so it has to spend a certain amount of time, at least, outside of this totally geodesic part. And it's a very explicit estimate. So we're out of time. Thank you very much.